After selecting a model, the next step is to look at how to train the model. Along with that, we can look at a few key concepts used inside a model. As mentioned before, the function is the model. If all the data points can be fit into the function, then the function can define how your data is represented. In the example graph, the red curve shows an approximated model of the function that fits all the given input data points. Notice in the graph that the function models all the data points closely, but does not accurately represent all the data points. As more data is available, the weights of the function are adjusted to model the data better and better. The weights of a neural network are typically solved using a process called training. The goal of training is to adjust the weights so that the network can accurately predict the output for a given input. There are a few different techniques for training a neural network. In the example, weight is the slope of the line. The correct weight gives you the exact line for the data represented by the function. After trying a few random weights, you'll notice that the weight of 2 is closest. You can then move into fractional values to arrive at y equals 9/5 x plus 32, which is how you convert Celsius into Fahrenheit. Therefore, even known functions can be verified using neural networks. Even if the nonlinear function can be broken into a bunch of small linear functions, it turns out a simple addition of linear functions cannot become a nonlinear function. Therefore, we use activation functions to introduce nonlinearity when learning the data that cannot be linearly classified. A simple ReLU function is commonly used for activation, where when x is negative, y is considered 0. Otherwise, y is the same as x. You can separate the orange data points using a simple line. Or you can draw a curve to select all the oranges perfectly. Overfitting is a side effect of trying too hard to fit all the test data, but it ends up being no help when it comes to new data. Overfitting uses a more complex model and thus more storage. You can gather more data to help. Gathering more data requires more time and increases your memory requirements. Question remains, can you gather more data? Also, notice here that an infinite number of lines could be drawn to separate the data shown in the graph. But which line to choose? To determine the best decision boundary, we can employ various classification algorithms. Depending on the complexity of the problem and the number of features, several classifiers can be tested and chosen from the simplest or the more expensive ones. Linear classifiers try to find a function such that the decision boundary is a line. When such boundary is harder to define, you can choose other classifiers. Density estimation is a Gaussian distribution of the input data points. The k nearest neighbors, as the name suggests, find the k neighboring data points and determine the classification of the current data point. Support vectors are the defining vectors that separate the classes via a hyperplane. Support vector machines identify the support vectors and maximize the margins. In this example, originally, we used 3 features. Visually, the data on the left is thickly clustered. What if in the example shown, sweetness and acidity can be combined into a somewhat oversimplified taste feature? In doing so, we reduced the dimensionality of the input features from 3 dimensions to 2. By reducing the dimensions to 2, we could more easily classify most of the orange data points. Principal component analysis is commonly used for dimensionality reduction. Kernels are used for pattern analysis between inputs to generate a simpler input to the next layer or stage of the neural networks. For example, in image classification, you can use a kernel to capture different types of local features such as edges, corners, and textures. Images have pixels, and each pixel is a vector with components of RGB. By placing the kernel over each 9x9 grid of pixels and multiplying the RGB data at each position, you can blur the picture. Even if most of the data doesn't fit perfectly into a curve, function simplification is necessary to simplify the model and reduce the complexity of calculations and the storage requirements. When approximating the functions, your predicted results tend to deviate from the actual data. This deviation must be minimized. Minimize the loss to zero for every data point to model the data accurately. You adjust or tune your parameters to find the global minima for the loss function. Stochastic gradient descent is one of the methods to minimize the loss function.